Bismillahirrahmanirrahim. Welcome to lecture number 11 of Advanced Computer Architecture. The topic that we cover is mapping functions. So we will have an introduction to cache memory. We will discuss how do we map memory data, like data in the RAM, to the cache, and how this mapping happens, like what are the different techniques that we use for this mapping. So number one, this is introduction to cache memory. So main memory is larger in size than cache generally. Like if you look to this current computer, so we normally have RAM from 6 to 8 GB. And cache is very small, maybe in megabytes. So we cannot load the whole data like 6 GB. Let's assume that we have 6 GB RAM and we have 1 GB cache. So we cannot fit this 6 GB RAM to 1 GB. We need some mechanism. How do we load data from RAM, and how do we make space in the cache so we move data to the RAM? So we cannot fetch all the addresses of the main memory to the cache at a time. We fetch only a limited number of main memory addresses to cache line. When other address need to be fetched in, we can take out the address from the cache, store in main memory, and load the new address from main memory to the cache. So these are certain mapping functions. Because there are fewer cache lines than the main memory, one technique is direct. It's a very simple technique, and it maps each block of main memory into only one possible cache line. We will discuss this direct mapping in detail. Associative, and this is a short definition of associative. You can read this. Set associative, and this is a short definition of set associative. We will discuss all these techniques in detail. So this is direct mapping. In direct mapping, it maps each block of main memory into only one possible cache line. And this is the expression like I is equal to j modulo m. I is cache line, j is memory block number, and m is number of line. So memory block number modulus number of cache lines give us a cache line number. This is, for example, our cache. This is main memory, and this is cache. So we are mapping every line to every line in the cache memory. Here we are showing only first m blocks. We are not showing the entire main memory, only m blocks, and they are mapped to cache memory. And if we have the full data, so then we need to have the modulus operator. So let's take an example. This is our main memory, and its size is 64 bytes, and number of words per block is 4, and number of blocks are 16, 0 to 15. So we have 0 to 15 blocks, and in the cache we have only 4 blocks or 4 cache lines. So how do we load this data? So 0, 1, 2, and 3, because 0 modulus 4 is 0, so 0 is mapped to 0. 1 modulus 4 is 1, so 1 is mapped to 1. 2 modulus 4 is 2, and 3 modulus 4 is 3. But 4 modulus 4 is 0, so this 4 will be mapped to cache line number 0. 5 modulus 4 is 1, and it will be blocked here. So that's the basic technique, direct mapping. And how do we know? So these are 64 words. So for 64 words, how many bits we need? It's 6, because 2 power 6 is 64, right? So these are our 64 bits. And for the main memory, we use these least significant bits as block offset, because there are 4 words per block. So we need only 2 bits, because 2 power 2 is 4. And for the block number, we are using 4 bits. 2 power 4 is 16, and you see there are 0 to 15, so 16 blocks. From the cache memory perspective, we use these 2 bits, least significant bit, as block offset. So we have 4 blocks or cache lines. This these 2 bits, they are using um, line number. So these are block offset, and these 4, 1 2 3 4, these are line number, and tag number is actually this tag number. So how do we compare? I will explain this in the diagram like this. Yes. So let's assume we get a memory address. What we do, if we want to know the word, so we get these W, least significant bits, and we compare it with, so first we take the tag line, we get the tag number. So line number gave us to this full block. We get the tag number, we compare this tag with this tag number, and if they are the same, so then it means it's a cache hit. It means that the data exists in the cache. So then we can access corresponding word by going through the given word. So this memory mapped, this main memory is actually mapped to cache, and this cache is actually accessed using this distribution of J modulus M. All right, so these are the direct mapping summary. So I explained this example with the 64 word main memory and 16 word cache memory, but this is more general for the W and the S, so I hope you can go through it. Now, what are the problems? The problem is that the advantage is actually that it's simple and inexpensive to implement. But the problem is that 2 words mapped to the same line in the cache will continuously fetch n and take out from cache even if we have a free line. For example, 0, it is mapped, block number 0 is mapped to cache line number 0. Similarly, block number 4 is also mapped to cache line 0. So if I'm continuously loading 0 and 4, so it means I will first load 0, then I need 4, so I need to put the cache memory back to RAM, the block number, and then I need to load 4. Then I need 0 again, so I know I need to offload block number 4 to main memory and need to load block number 0. Even 1 2 3 cache lines, they are empty. This is called conflict miss. And victim cache, it's actually proposed as a technique to deal with this conflict miss in direct mapping. It's a fully associative cache, and typical size is 4 to 16 cache line, and it's residing between direct mapped L1 cache and the next level of main memory. So we have L1 cache is direct map, and victim cache is L2 cache. So that's associative memory. So it allows each main memory block to be loaded into any line of the cache. So we are not mapping one block of RAM to one cache line, but we can load any block number, any block number to any cache line, like it can be loaded anywhere. So the simple formula, again, we are taking the same example. We are taking these two least significant as block offset and 4 bits as block number for the RAM. This is the same as previous, but now we are using 4 bits for the tag because we have these are the 4 bits. So 4 means 2 to the power 4 means 16. So we can load 16 words. So for example, 0 can be loaded to number 0, number 1, number 2, number 3. depends whatever is available. So that's how we compare. We get a memory address, we get a tag, and we compare with all the tag in the cache line. And if any of the cache line is hit, it means the data exists in the cache and we can access data. Otherwise, we need to load it from the RAM. So this is more explanation. This is an example in the book. I hope you can read it. And then it's a summary. It's the more general form. I explain you with the very small numbers, but these are very general, so you can understand. Now, the problem with associative mapping is that we resolve the problem of conflict misses in direct mapping, but we need n comparators. If we have 4 comparators, so we need to compare 4 times. And if we have 1,000 comparators, so we need to compare, uh, I mean, if we have 6 bits, so for 4-bit, we need to compare 4 times. For 6-bit, we need to compare 6 times. And for 32 bits, we need to compare 32. So the hardware cost is increased. The hit latency is increased because of the number of comparators and the OR gate. And in case of cache miss, a replacement algorithm is needed. What is replacement algorithm? We will discuss this in detail. So a mid solution that we are currently using is set associative mapping. So direct mapping is simple. Associative mapping is simple in a sense that we resolve the problem with the direct map, but we introduce more problems. So the middle point is set associative. So we divide our cache into different sets. So within the set, the mapping is direct mapping. Like we can go to, like we know that one word will go to set number 0. Or for example, word number 4 will go to set number 0. But within the set, it can be anywhere. So within the set, it is um, associative mapping. So that's an example. For the cache memory, we have set 0. It means that this block can be loaded anywhere, and this block can be loaded anywhere. This is an example. For example, 0. 0 modulus 0 is 0, so it will load into 0. 1 modulus, we have 2 sets. So 1 modulus 2 is 1, it will be loaded into 1. 2 modulus 2 is 0, it will be loaded into this set, anywhere in this set. 3 modulus 2 is 1, so it will be loaded anywhere here. So this is again the top 6 bits. This is the configuration for the RAM. The bottom one, we are using this 1 bit for the set because we have 2 sets depending on how many sets you have, and then we are using 3 bits for the tag. For 3-bit means that 2 to the power 3, so it means that we can load 8 words to cache. This is the comparison. So now we don't need n comparators. We are comparing only those tags which are inside the set. So the number of comparison is reduced compared to associative mapping. And this is the summary of associative mapping. These are different cache sizes. So we have these are 2 direct mapping, 2-way associative, 4-way associative, 8-way associative, and 16-way associative. And you know that the black line, when we have, for example, 1K, so direct set associative, it's the performance, the hit ratio is very low. But as we increase the cache size, for example, for cache size 32K, direct and 2-way associative has lower hit ratio, but the hit ratio is increased for 4, 8, 16. And I think it's increasing until even if we have 1 megabyte. So direct mapping and 16-way set associative is same. So the point is that as we increase cache size, we increase the hit ratio. And as we increase the associativity, We also have better hit ratio. These are the comparison of direct, associative, and eight-way. It actually demonstrates how many comparators do you need, and size of the tag, and number of lines, and size of the comparator. So associative is like 22, direct is 10, but four-way associative is 12. 12 comparators are size of the comparators. So this demonstrated set associative memory is the most efficient technique, and this technique is used in recent architectures. Thank you very much.